Hello and welcome back to the deep dive. Today we're putting on our lab coats, metaphorically at least. We're going to be tackling a topic that sits right at the heart of Class 12 chemistry, specifically Unit 5.
And it's a unit that, it trips a lot of students up. It requires a real shift in how you visualize atoms and how they interact. We're talking about coordination compounds.
Right. And to get us started, I want to pull up a very specific memory. I'm guessing most of our listeners have done this practical in school. You're standing at the workbench, it smells faintly of chemicals, and you're holding a test tube with a pale light blue solution, copper sulfate.
Ah, yes. A classic starter for salt analysis or functional group tests.
Exactly. Then you pick up the ammonia bottle, you add a few drops, and suddenly it feels like magic. That pale, watery blue just transforms into this intense, deep, royal blue. It's almost glowing.
It is a beautiful color.
It is. But then, and this is the kicker, if you add some acid to it, the color just poof, it vanishes. It fades right back to the original pale blue.
It's arguably one of the most visually satisfying moments in the lab practicals, that whole sequence.
It really is. But here's the question that keeps coming up in the notes we're looking at today. Why? I mean, why does that happen? It's not just mixing paint, right? We aren't just making a darker blue by adding dye.
No, not at all. Something fundamental is changing at the atomic level.
So you're witnessing a change in the actual molecular architecture.
Absolutely. What you're seeing is a specific type of chemical bond forming and breaking in real time.
So that's our mission for today. We're unpacking bonding in coordination compounds. We're going to look at the mechanics, the nuts and bolts of how these things actually stick together in coordination chemistry.
And I'm glad you used that word, mechanics, because usually when we learn bonding in, say, class 10 or 11, it's very black and white, positives attract negatives, done.
Right, ionic bonding, like two magnets just snapping together.
Exactly. But if you rely only on that logic, coordination compounds make absolutely no sense. Here, you have positive metals somehow holding onto completely neutral molecules.
That's a great point. Ammonia is neutral. It has no charge. Why would a positive copper ion even care about a neutral ammonia molecule?
That is the exact puzzle we're going to solve. This deep dive is about understanding the coordinate covalent bond. If you get this one concept, you basically unlock the whole unit.
Okay, let's strip away the jargon for a second. If I'm a student sitting in the back row, maybe I missed the first 10 minutes of the lecture and I'm just trying to catch up. How do you explain this bond at the absolute zero level?
At the simplest level, think of it as a gift.
A gift.
Yes. You have two players. You have the ligand and you have the metal. Now, the ligand is the donor. It's holding a pair of electrons, a lone pair that it's willing to donate.
Okay, so it has something to give.
And then you have the metal. The metal is the acceptor. But it's not just grabbing electrons from anywhere. It has a specific empty orbital. Think of it as an empty pocket or an empty parking space.
So the ligand has the electrons and the metal has the space for them.
Precisely. The bond forms when the ligand donates that pair of electrons into the metal's empty space. But, and this is the crucial part, it doesn't give them away completely.
It's not a complete transfer?
No. It is a covalent bond, and covalent means sharing. The ligand puts the electrons into the pot, but once the bond forms, both the metal and the ligand share them.
That's a really interesting nuance. Usually in covalent bonds, like say in a carbon-carbon bond, I bring an electron, you bring an electron, and we share. It's like a potluck dinner.
Right. A standard covalent bond is a potluck. We both contribute one dish to the meal. A coordinate bond is, well, imagine I invite you to dinner, but I cook all the food.
I see where you're going with this.
We still sit down and eat it together. We share the meal equally, but I was the one who provided everything. In this case, the ligand provides both electrons for the pair. The metal just provides the empty plate.
I love that. Let's deepen that visualization because the source material uses this great concept of empty hands.
This is probably the best way to picture it mentally, especially for an exam. Imagine the metal atom, say, a copper ion or an iron ion. Picture it just floating in space. Now, visualize that it has these empty hands sticking out.
And those are the empty orbitals.
Correct. It's just standing there, hands open, palms up, waiting. It can't grab anything on its own. It needs something to fill those hands.
And here comes the ligand.
Well, the ligand approaches. And the ligand is carrying a physical object, a package. That package is the lone pair of electrons. It's a pair of electrons that isn't busy doing anything else.
So the ligand walks up, places this package into the metal's open hand, and then what? They clasp it?
They clasp it tight. The ligand's hand, which is holding the electrons, and the metal's hand, which was empty, they lock together. That interlocking grip is the bond.
That clarifies the roles so well. The metal needs that empty space. If the metal didn't have empty hands, if its orbitals were already full of its own electrons, this wouldn't work.
Exactly. And if the ligand didn't have a gift to give, no lone pair, it also wouldn't work. You need both the giver and the receiver.
So if we had to crystallize this into a definition, the kind you need to write down for the board exams, what's the anchor definition here?
The anchor definition you must know is this. The coordinate covalent bond is formed by the donation of an electron pair from a ligand, the donor, to an empty orbital on a central metal atom, the acceptor, resulting in a shared electron bond.
Resulting in a shared electron bond. I want to double click on that because I feel like that is where the confusion really starts.
It is indeed.
I remember looking at the stuff and thinking, okay, the metal is Q2+, it's positive, the ligand is electron rich. Why isn't this just ionic? Why isn't it just static electricity snapping them together?
That is the classic misunderstanding trigger.
Yeah.
It's so easy to fall into that trap because we're conditioned to think metal plus non-metal equals ionic.
Right.
But you have to correct that thinking here. Ionic bonding is non-directional. It's just a fuzzy field of attraction like a magnet pulling on a paperclip. It pulls from any angle. A coordinate bond is directional.
Yeah.
It has a geometry. Remember the empty hands visual. You have to approach the hand from the right angle to place the gift in it. The orbitals stick out in very specific directions. The bond has a shape.
So it's structural. It's not just a clump of magnets. It's a built structure, like Lego bricks snapping together.
Exactly. Lego is a great way to think about it. You have to align the stud with the hole. If you come in it from the side, it won't click.
This actually leads us perfectly to the analogies in the notes. We talked about empty hands, but there's another one here called handshake. How is that different?
The handshake is great for understanding what happens after the bond is already formed.
Okay, walk me through it.
Imagine two people. One is the ligand. They reach their hand out first. That action of reaching out represents the lone pair being offered.
Okay.
The other person is the metal. They just have an open hand waiting. When they clasp hands, the bond is formed. Now, look at that handshake. Once they're holding hands, can you really tell who reached out first?
Not really. Once the hands are clasped, they look the same. They're just connected.
Exactly. And that's the deep insight here. Once the bond forms, neither person is giving or taking anymore. They're simply holding hands. The electrons are being shared. The history of how the bond started, who gave the electrons matters for the definition, but physically, it creates a connection that ties them together equally.
That is really helpful. It stops you from thinking of the metal as sort of stealing the electrons. It's just holding on to them.
Right. And there's one more analogy from the reading that I think clarifies the necessity of the fit, the electrical plug-in socket.
Oh, I like this one. It's very intuitive.
It is. Think of the ligand as the cord with a plug at the end. The prongs of the plug are the lone pair.
And the metal is the wall socket.
The empty orbital. Now, you can't plug a socket into another socket.
Yeah.
And you can't plug a plug into another plug.
Definitely not.
You need the male part and the female part. You need the electron density, the plug, to enter the electron void, the socket. That's what establishes the connection. If the metal doesn't have that empty socket, that empty orbital, no current flows, no bond can form.
So, ligand equals plug, metal equals socket.
As simple as that.
Now, I want to step back and ask a why question. Because science doesn't just invent terms for fun usually. Why do we need this special category? Why did chemists look at this and say, okay, we need a new name for this?
Because they were stumped. For a long time, there was a major puzzle that the old theories just could not solve. And that puzzle was, how can a positive metal ion bond with a neutral molecule?
Right, back to the ammonia thing. Ammonia has no charge.
Exactly. Standard ionic theory says opposites attract. Positive attracts negative. So logically, copper 2+ should attract chloride 1-. That makes perfect sense. But copper 2+ attracting ammonia 0, that broke all the rules.
It's like a magnet picking up a piece of wood. It shouldn't happen.
Precisely. So G and Lewis came along, the same Lewis of the Lewis dot structures, and he proposed this radical idea. He said, what if the bond isn't about charge at all? What if it's about lone pairs?
Ah, so it's not about being negative. It's about having spare electrons ready to go.
Yes. This theory finally explains why a complex like Q and ethers can stay together. It's not because ammonia is negative. It isn't. It's because the nitrogen atom inside the ammonia has a lone pair of electrons that acts like a hook.
That's the big mental shift. You have to stop looking for a charge and start looking for the hook.
That's the big takeaway right there. Shift your focus from charge to lone pairs.
Okay, let's make this cinematic. I want to build a mental movie for our listener. We have the analogies, but let's visualize the actual particles. I want you to picture a nickel ion, Ni2+.
Okay, let's float it in the center of a dark room. Visualize a bright, small, metallic sphere. That's the nickel. And all around it, visualize these ghostly, empty shapes like invisible balloons attached to it. Those are the empty orbitals.
And now, zooming in from the side, here come the ammonia molecules, drifting towards the nickel.
Focus on the nitrogen atom in the center of that ammonia pyramid. Imagine a little glowing blue dot on the very tip of that nitrogen. That blue dot is the lone pair.
The ammonia drifts closer.
Close. And the blue dot reaches out. It finds one of those ghostly empty balloons on the nickel. And snap.
It just clicks into place.
It slides right in. A glowing line. The bond forms between the nitrogen and the nickel.
And this happens multiple times, right?
4 times usually for a metal like nickel. Snap, 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 snap. 4 ammonias surround the metal in a specific shape.
And here's the beautiful part, the result. As these bonds snap into place, the color changes.
Yes, the complex might turn a vivid purple or a deep blue. This happens because those new bonds, those handshakes, they actually change the energy levels of the electrons on the metal. They change how the entire complex interacts with light.
So the color we see in the lab isn't just a random side effect. It is direct visual evidence that those handshakes are happening.
The color is the proof. If the bond breaks, the color changes back.
Which brings us right back to our opening experiment, the copper sulfate.
Right. So initially you have that light blue solution, that's KHOO. The copper is holding on to water molecules.
Wait, water can act as a ligand?
Of course. Think about the water molecule, HO. The oxygen atom has 2 lone pairs. It's a great ligand.
So the copper is holding hands with water molecules.
Yes. But then you pour in ammonia. Now, ammonia is a bit of a bully, or rather, it's just more attracted to the copper. Its nitrogen lone pairs are better donors than oxygen's lone pairs.
So it pushes the water out of the way.
It kicks the water out. The ammonia slides into those empty orbitals, replacing the water. We get QA. And because the handshake is different, it's stronger. The energy levels shift, and the color deepens to that royal blue.
And then the acid test. Why does the acid kill the color?
This is the real aha moment for chemistry students. When you add acid, you're adding protons H+ ions.
Oh, okay.
Now remember, ammonia has that lone pair, that plug. Protons, H+, are desperate for electrons. They're the ultimate empty socket.
So the ammonia suddenly has a choice.
It has a choice. Stay bonded to the copper or bond with this fresh, exciting proton that just arrived.
And ammonia loves protons.
It loves them. It forms ammonium, NH. So the ammonia literally lets go of the copper to grab the proton instead.
It breaks the handshake.
It breaks the handshake with the copper. And since the copper is now alone again, it just grabs the nearest thing available, which is all the water molecules.
And the color goes right back to light blue.
Exactly. The fading color proves that the deep blue was entirely dependent on the ammonia donating its electrons to the copper. Once you distract the ammonia with acid, the complex just falls apart.
That is such a satisfying logical loop. It really proves the theory. Now let's move from the test tube to something a bit more vital. Because we always ask, why should I care? Well, this type of bonding keeps us alive.
It does. We are talking about hemoglobin.
I think most people know hemoglobin carries oxygen, but I don't think they realize it's a coordination compound.
It is, at its core, a coordination compound. At the very center of that massive hemoglobin protein, there's a tiny iron-to-ion, Phe.
And I'm guessing it has those empty hands.
It has empty orbitals waiting.
And the ligand is?
Oxygen, the O molecule. Oxygen has lone pairs. When you breathe in, O enters your lungs. It acts as a ligand, it floats up to the iron, and forms a coordinate bond.
So my breathing right now relies on a ligand donating a lone pair to a metal ion.
100%. But here is the key. It has to be a reversible bond.
Reversible.
Think about it. The handshake needs to be firm enough to hold the oxygen while it travels through your blood all the way to your tissues. But when it gets there, it has to be able to let go.
Ah, right. If it was a permanent superglue bond, you'd suffocate.
Exactly. If the bond is too strong, it never lets go. That's actually why carbon monoxide poisoning is so deadly. CO is a much stronger ligand than ORO. It outcompetes the oxygen, grabs onto the iron, and then refuses to break the handshake.
Wow. So coordinate bonding is quite literally a matter of life and death.
It's not just some dry textbook stuff. It is the machinery of life.
I want to touch on one more specific point from the notes before we get to our summary. We've mentioned it briefly, but I want to make sure it sticks because it seems to be a common trap for students. The neutral ligand issue.
Yes, this is probably the biggest mental block.
We established that ammonia is neutral but bonds well. What are some other neutrals we need to watch out for?
Water, HEO, is a big one. Carbon monoxide, CO, is another. Ethylenediamine, which we just call N, is another one. All completely neutral.
So if I'm a student looking at a molecule and wondering, can this be a ligand? I should not be looking for a minus sign.
Oh, stop looking for the minus sign. Look for the dots.
The dots.
The Lewis dots. The lone pairs. If you see an atom like nitrogen or oxygen or fluorine, and it has a pair of electrons just sitting there unbonded, that is a potential ligand.
That's the rule. Don't look for the charge, look for the dots.
That is the golden rule.
Okay, we've covered the visualization, the analogies, and the real-world examples. Now, I want to transition to what we call the exam-safe clarity lines.
The must-knows.
Exactly. If our listener is walking into an exam hall tomorrow, what are the sentences they need to have locked and loaded? Let's go through them one by one.
Okay, let's slow it down. Clarity line number 1. A coordinate covalent bond forms when a ligand, the donor, donates a lone pair to a metal, the acceptor.
And the tie back there is simply ligand equals donor, metal equals acceptor.
Right. Clarity line number 2. Once formed, a coordinate bond is indistinguishable from a standard covalent bond.
Meaning, once the handshake happens, it's just a bond. Don't overthink the history of how it was made.
Exactly. It's all about shared electron density holding the atoms together.
Got it. Clarity line number 3.
Neutral molecules like ammonia and water can be ligands.
And the tie back. Do not look for a negative charge, look for the lone pair.
Precisely. And that leads to the final, and maybe most important one. Clarity line number 4. Ligands must have at least one atom with a lone pair.
So no lone pair means no coordination.
Correct. If you have a molecule like methane, CH3, carbon has used all its electrons in bonds. There are no lone pairs. It cannot be a ligand. It has no gift to give.
No gift, no handshake.
No bond. It's that simple.
That is extremely clear. So let's wrap this up with a short summary of our journey today. We started with the core idea.
The metal has empty pockets. The ligand puts the electron pair gift inside those pockets.
We use the analogy of the handshake.
One person reaches out, that's the directional nature, but once they clasp, both hold on. It becomes a shared connection.
We looked at examples, from the beautiful blue color of copper ammonia in the lab all the way to the oxygen hitching a ride on iron in our blood.
Which shows that this type of bonding is happening everywhere, all the time.
And the key rule we just established, it's covalent, it's about sharing, and it absolutely requires a lone pair.
That sums it up perfectly.
Before we sign off, do you have a final provocative thought for our listener? Something to let them mull over while they're walking to class?
I do. It's a bit philosophical, I suppose. We spent all this time distinguishing a coordinate bond from a covalent bond, right? We made a big deal about the fact that the ligand gives both electrons.
We did.
But think about this. Once that bond is formed, once those electrons are swirling around both nuclei, does the atom actually remember where they came from?
That's an interesting question.
If you took a snapshot of the bond after it was made, could you tell the difference? Or is the term coordinate bonding just a label we use to describe the history of the bond, rather than the physical reality of the bond itself?
That is a deep thought. It's like asking, once you pour water into a bucket, does the water remember which tap it came from?
Exactly. Does the history define the bond, or does the shared strength define the bond? It's something to think about.
Well, on that note, thank you so much for joining us on this deep dive into Unit 5.
It was a pleasure. Happy to help.
And to our listener, next time you see a complex formula with brackets and metals and ammonias, don't just see letters and numbers. Try to visualize those handshakes, see the gifts being given. It makes the chemistry a lot more human. Thanks for listening.